I recently launched a TVC rocket, and this is the breakdown of what probably went wrong. I'm not sure yet, but there are a lot of things that went right and a lot of things that went wrong. Okay, let me show you. The This is the data I got from the flight, and we got a lot of good data. The computer calculated the correct yaw pitch roll angles. It got its orientation calculations. It even calculated the correct servo commands from the PID controller. So as you can see from the roll and Y axis, we see that we have a command, the orange line, and our corresponding angle for that command. But we send out the command, but the rocket isn't responding at all. So something in here probably went wrong between sending out the command and receiving and actually doing something with the command. If we take a look at the close angle camera and slow it down the video, we can see that the rocket will turn to the left, but have no intention of actually correcting it. So we calculate a correct command, but as you can see, the flame is going straight down and not correcting to the correct um, direction. So the problem probably lied in the commands to the servo. So I thought, what makes a servo rotate? What's the command behind it? And it turns out the servo should receive every 20 milliseconds a command, and depending on the width of that pulse you get, the servo will rotate a different amount. More specifically, with a 1 millisecond pulse, the servo will rotate to 0 degrees. A 2 millisecond pulse will have an 180 degrees, and then everything in between will get mapped. So I also use the SoftwareSerial library for my radio module to get and receive data from the rocket. And this library uses interrupts. These interrupts will stop the timer from the servo and add a small delay, which, depending on how big the delay is, will rotate the servo by a different amount, even though you don't want it to. So you send out a 1.5 millisecond pulse, but it actually gets a 1.7 milliseconds response. And so this was the problem I was dealing with the servo jitter. And when you take a look at the close cam before launch, if you take a look at the top servo motor, that's the motor I didn't fix the problem on because I thought only the important thing was the TVC mount and the servo motors there. But if you take a look, the servo will jitter, yeah, like this. So the jitter is because of these interrupts. And how I thought I would solve this problem was by doing this. So this is how my code was first structured. The servo commands came all the way last, but the servo library actually works under the hood. So the servo commands get sent out at all times, basically, and that's why we can have an interference with the interrupts from the data update. So what I thought I would do was just detach and attach the servo before and after the data update. And this solved the jitter. This completely eliminated it, but it's not a good solution because the servo detach and servo attach actually pull out your commands to the servo, which is what I thought I wanted, but you basically lose control of your servos for a big portion of your flight. And this is a solution I actually used to fly with, which is, now that I think of it, not good. And then something else I could think of was to use different library. So the PWM server library claims to be immune to interrupts, but unfortunately I couldn't use this library with the chip I was using. I'm using the Arduino Nano Every chip, and this is a Mega AVR architecture, and this library wasn't compatible with it. So instead of trying to fix this library and try to make it compatible with it, I wrote my own small code, um, which really sections off the command part, so it doesn't spill out and make an all interrupts mess. And the way I did this was by using this simple code, uh, basically a digital write of the servo pin, and then waiting a couple of microseconds, and then dropping the pin low again. And this every 20 milliseconds. So I basically manually send out the servo commands. At first, I mapped the angle from 0 to 180 degrees, 2,000 microseconds to 2,000 microseconds. And this range you can tweak to really hone it down to your specific servo, because some servos use 500 microseconds to 2,500 microseconds or something in between. So this is some calibration that you can do in your own. This was probably what caused my flight to fail, but there's another thing I fixed while looking for the problem, and that's increasing my loop time, so decreasing my loop time and increasing my loop frequency. So I launched with a 15 millisecond loop time, which is a 20 hertz update cycle, which is not enough really to, my simulation said it was enough, but you really want to give yourself some more margin. And so I was able to increase my loop frequency to 20 to 50 hertz, so 20 millisecond time. And the way I did this was by looking at the code I was running and then timing every part of the code and seeing where a lot of time was wasted, quote unquote. And with it, that's when I found my get IMU function wasted around 25 milliseconds. And I thought this was very, very weird because this part of the get IMU function only uses 1 millisecond. So the problem lies with this thing right here. And this function right here is this basically waits until the DMP from the MPU 6050 sends out a packet with its orientation data, and only then it enters this other piece of software. So what I did was implement it in my actual loop. So this is the whole function which makes the rocket correct itself. And we now not only look for our 20 milliseconds that have passed, but we also already ask for the latest package from the BMP. So this way, it somehow increases my loop time. And so now I'm able to control my rocket at 2.5 times the speed, which is very, very good. By the way, this will allow for a much more aggressive control algorithm because when you have your updates more frequently, you can look what your corrective action needs to be more frequently. While if your loop time is much slower, you have to be more careful with overshoots because if you have a very aggressive algorithm and your loop time is slow, you might want to you might want to correct very hard, but by the time that you can see your corrective action and know when to stop, it might be too late already and you have overshoots. And what I also did was decrease my pyro on times. So when you take a look at when the rocket fires, it certainly doesn't need to be 1.5 milliseconds on before the rocket will leave the pad. And it more likely has around 200 milliseconds of pyro on time, which should be more than enough to ignite the rocket motor. So that was the breakdown of my first flight of my TVC rocket. It did a lot of things wrong, and it did a lot of things right as well. And I will try to launch again this weekend, and with all the improvements made, we'll see how it goes from there.